now machine learning is everything for us at H2O. And finally, we can combine the two. And who here has used GPUs in their lives or in their work lives? Okay. Who here has done machine learning? Pretty much everybody. Have you done the same things with H2O yet? Probably some of it, right? Maybe some machine learning, but maybe not quite GPU machine learning yet. Have you done deep learning? So yeah, a lot of people have done deep learning. It's one of the killer apps for GPUs, as you can see from NVIDIA stock price. And we actually work with NVIDIA now on bringing machine learning to GPUs. The goal is to populate those DGX-1 supercomputers with like cool machine learning algorithms that are doing more than just deep learning. Because we still believe that with good statistics and good data science engineering, you can actually do better than the deep learning on many data sets. If it's not image related or text or something, it's just transactional data sets. So this is a quick introduction to the philosophy of H2O and the product and the big picture, basically. So let me take this chair out of the way, show you these slides. This was presented last week at the GTC conference, the NVIDIA GPU Technology Conference. And the company is roughly 60 people, maybe 65. I'm Arno Candel, a CTO. And we actually have one more person that is at least affiliated with H2O as a contractor. That's Rory Mitchell. He's from New Zealand, and he's here for 2 weeks. And he actually wrote the GPU plugin for XGBoost. So applause to him. It's a nice effort. That's the first effort to bring GPUs to gradient boosting, which is a very powerful concept, right? There might have been other people doing stuff, but this is the most popular version of gradient boosting, as you know. And what we showed last week is this following video. I think it would be fun to show you too.
But Holland comes in for a pit stop. Time to refuel and change tires. Newmore himself changes the tires. Only 4 crew members, including the driver, are allowed to work on the car. It's a tense time. Holland stays in his seat, anxious to get away. Let's watch. Changed at last. A crewman polishes the windshield as Holland moves away just 67 seconds after he stopped.
So yeah, it's fairly obvious, right, why you would want to have speed. This world is dominated by people who want to get things done, and time is the only non-renewable resource, as we like to say. So this is another video we presented. This is our GLM algorithm running our GPUs. On the left, you can see the GPUs we use. This is 8 GPUs on a DGX1. On the right, you have a workstation with 2 Xeon chips. You can see the number of models trained. So here we're already doing 1,000 models, right? And then 100 models a second or so. So it takes only about 100 seconds or so to build 4,000 models. And these 4,000 models are basically exploring the generalized linear modeling space of regularization type and regularization space. These are linear models. Actually, our studio has been doing an idea of putting little charge lights behind it, but since the movie was the heat on and space, obviously using it still kind of makes fun of the CPU if you want, right? But it still hasn't done anything yet. It's still doing the grand computation of A transpose A, so A is the data matrix. And now you see the first models coming in 4, 5, 6, and so on. So it's about 100 times slower or 50 times. And we have different versions of this video up there with like time lapse and all that. But you can see the speed up here. I think it's 45 times or 35 times slower on this box. Depends on the GPU, the CPU. So they're basically saying GPUs are useful if you know what to do with them. However, the best model that you saw at the bottom there was the 8 GPU version of the GLM. That's this guy here with 100 seconds that you just saw live, right? We can do the same almost, only 3 times slower on a CPU. But that's a different algorithm. So now the question is, can we make that algorithm also run on the GPU, right? And then it become another 50x faster or something. And the answer is probably yes. So they're going to work on that as well. But basically, now that we have CPUs and GPUs and we understand the algorithm, it's kind of fun exercise to port it to the GPUs. So the next decade will be probably dominated by GPU computing, especially for this kind of workload. Now this is what we're going to talk about today, gradient boosting. And this particular benchmark has been using XGBoost. And we're actually using XGBoost from inside H2O for this benchmark. So H2Boost is a C++ algorithm that's calling out the CUDA on the GPU, and H2O is a Java application. And from Java, we're sending the data via the Java native API, JNI, Java native interface, I should say. We're sending a float array down to the C code, basically. Let's say go to the GPU, do what we need to do. And then it goes into Rory's algorithm and runs that much faster. And now he wrote another algorithm that's even faster than this. You can look at that today. So there's a video on all that. These slides are posted on our SlideShare account if you want to see them, but it's also a GitHub repository here. That might be the easiest way to look at this stuff. The GitHub repository is called H2O AI/perf for performance. So there's a notebook, and there's videos and so on. And why are we doing this stuff? Well, because the next gen of our product will not just be algorithms to build these models, as you know from H2O so far. That's what we've mostly been focusing on. But the next gen product will actually be a self-driving AI. So it will be an engine that does the munging, the data science, the data engineering, the evaluation of these pipelines, the interpretation of these models, or the model interpretability will be important. You want to understand why this new feature that you engineered, is it working or not? You want to know what the outliers are. You want to know what's holding back your loss from getting better. Maybe you have duplicate rows that have different responses, right? There's just no way to predict it any better. So we have Kaggle grandmasters. We actually have some of the top Kagglers in the world working for H2O. We have professors, Stanford professors, and actual professors in the office. We have world-class system engineers. They're putting all this together to have this engine just train models as fast as possible. If you get a 10x speed up from the GPU, you'll take it. So that's the idea. And now here's another cool video of a work in progress, which is a data table. You know R's data table? Has anybody here used R data table? So that's Matt Dowell's product, and he works for H2O as well. So this is a little demo. I think we can run it in 2x the speed. What will do this? So he's loading a 32 gigabyte data set onto a 16 gigabyte laptop instantly, going to a random place in the data set, applying arbitrary filters, selecting a subset of the 157 million rows after filtering. All of this is happening almost in real time because it's compiling down to LLVM and it's using memory mapping of the data on disk. So you're only accessing the columns that you're doing the query by, you're only accessing these like linearly or something with prefetching and all that, so it's very efficient. So it's a very cool project that's going to help us with the munging, but currently, of course, it's not ready yet for actual use, it's all a prototype, so it's basically our hopes for the future is to have a really fast munging engine as well. That's Pythonic and able to scale also on GPUs eventually, because this can be ported to GPUs. And this is how it's going to look like. Maybe that's just one of the many ideas we have for the front end. So the goal is to have few buttons to press as a user, but many things that show up. Like an airplane that flies, you want to see what's the tank, you know, what's the velocity, what's the map and all that, but you're not supposed to like control it yourself all the time. It's like an autopilot. And we have lots of customers that are happy with this, and they like the outlook, and everybody's really excited about going to GPUs and doing fast machine learning. And you can imagine that banks and insurances and healthcare industries and so on are very excited about more and more munging, because to this day humans are still the problem, right? They don't know what to do with the data, they don't know what features to engineer or not, or how to clean the data. There's a lot of ugly stuff out there that you have to take care of, and we're not going to solve all these problems, but at least maybe we can avoid some of the pitfalls. If the data is not IID, we do an 80-20 split, for example, you might not want to do the whole experiment because it's useless, and we can prevent these things. So this is the roadmap for GPUs, and today we're going to talk about basically this here, GBM single GPU, and maybe GBM multi-GPU, where we will build multiple models on multiple GPUs at the same time. But we're not building one model on multiple GPUs. That's on the roadmap. All right, so let's go to this notebook. The notebook actually is sitting in GitHub. Sorry, I can't type with one hand. So github.com/h2ai/perf. I showed you earlier. In this GPC folder, there's going to be the files that I showed earlier with the videos and all that. If you wanted to see it again, and notebooks and pip install instructions, so you can run a multi-GPU XGBoost on your DGX1 if you have it, or on your desktop at home with 4 GPUs or 1 GPU or 2 GPUs, whatever you have. This is this script here. And I tried earlier to launch a DGX1 on Nimbix, our cloud provider that we partner with, but the DGX1s were busy, so we can try it again later and see if we get one. We can then do a live demo on that. Otherwise, you'll just have to live with this. So here's a pip install instruction. The wheel is on S3, so it's public. You can download it and install it. And then the script will say download this Higgs data set from this other URL. Who knows the Higgs data set? We've done some studies. So there's 29 columns with all numbers and 11 million rows. So we're just using the first one, almost 10%, the 1 million rows. We're making a little method here that says run H2O XGBoost estimator. That's now a new XGBoost, a new addition to the H2O model family. So you don't just have GBM, GLM, random forest, and so on, but you also have H2O XGBoost, which then calls down to Rory's code if it's on the GPU, or just Tianqi's old code, let's say, plus all the collaborators' code, of course, that have worked on this super great code for the last few years. And that's really good if you have sparse data or if you have custom loss functions and so on. We don't currently support custom loss functions yet from H2O, though. So if you want the full control, you still want to use the native Python version that's written by the XGBoost community. But if you want to do an ensemble inside of H2O, for example, with other H2O algorithms, or you want to call it from R or from Flow, then you can do it this way. And I'll show you a live demo later. So in this case, we actually submit to a executor pool jobs in parallel. And we say we have 8 GPUs, so we can have 8 jobs running at the same time. And we just submit them all in a for loop and say push, 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 push to the worker queue. Here we submit, and all these models then get run in parallel because they have a different GPU that they're using. So we were passing a number saying you run on GPU 1, you run on GPU 2, you run on GPU 3, and all go at the same time because we have 8 GPUs. So this script actually submits them all, and at the end you wait for them to finish, and then you get the result. So it's kind of a nice little utility in Python. We didn't write any of this, right? We just made a method and said submit, submit, submit. And each one gets a different number, and the number is saying on which GPU do you want to run. And Rory luckily added that feature in the XGBoost plugin that says you're running on GPU 7. So we just have to pass a different number, and that's it. So now we can run this script, and out comes this amazing scaling, basically. Because
each GPU sees the whole data set, or you give
yes,
a portion
yes,
of the data set?
each GPU sees the whole data set. So that's the limitation right now, but also that gives you the perfect scalability. However, with Rory's new algorithm, this, by the way, is based on sorting the data, which is not as easily parallelizable across GPUs. Now, the new algorithm he wrote is using histograms. It's the same as H2O. So there you can, each node or each GPU can build histograms of the local data, and then they can reduce those histograms. So, for example, you look at the data that you have, and you look at the data that you have, right? And you are looking at how many people have age 7 to 9 or something, and you count that up. And it's the same thing with people 9 to 11 and so on. And in the end, you have a number for each bin, and here's a number for each bin, and you just average and put them together, basically, right? You sum it up.
You're sorting them by one,
you need to know where you cut. And
right.
you need to do this for every column.
feature you do
Yes.
sorting.
Yes.
There are a lot of features.
You don't need to sort, really. You just
you
need
do
to know.
something in the old algorithm, and then you're basically quantizing the features.
Oh.
Yeah.
So you know upfront where the cuts are. So you know 7 to 9 is a bucket, and 9 to 11 is a bucket. So when everybody says, oh, here's a new observation, what's the age? Oh, it's 17. Okay, it goes to bucket 7, right? You just add some numbers to that bucket. Now, what numbers you collect, that's the secret if you want, that you have to compute a Hessian and the gradient of some loss function. And those two numbers are what is collecting on the GPU. And it's basically related to what the histogram method does on the CPU as well. It's just slightly different implementation. But that's the math that's required to compute the statistics that you then need to figure out the right split points. So if you want to know more about the gradient boosting algorithm, you have a link for that too. So instead of going to GTC, you go to XGBoost in this perf directory, and that's the script we prepared today. This is the benchmark script we're going to look at today. So XGBoost itself is a widely used package, as you know, and it has been starred 7,000 times and forked 3,000 times. So a lot of people like that, and it's used for Kaggle, right? Who here has done Kaggle challenges before? Not too many, a handful of people. So Kaggle is this data science competition, right? And if you want to win this competition, you really have to use XGBoost. It's almost a mandatory thing these days. if you're really, really smart, you can get away with it, some other algorithm. You can use H2O as well, by the way. It's roughly the same as XGBoost, but XGBoost is widely used because it doesn't require this Python, it doesn't require Java environment. You can just run Python script. Our H2O is better suited if you have like a cluster of 10 nodes in a Spark environment and you're running on a 100 or 500 gigabyte data set, and it actually might be better than XGBoost. But they also have a distributed version. It's just a little harder to run. We make it basically easy to run, and also we make it easy to handle categorical values out of the box. You don't need to do any one-hot encoding or anything. It just works because we have these different schemes internally that we can apply. But XGBoost is like the tool for the super masters if they know what they're doing on medium-sized data, especially if it's sparse, because H2O does not have sparse support right now. So if your data set is 1% filled, the rest is all zeros, XGBoost is going to be much faster. So here's a lot of things that they're saying how it's working, right? I wrote this whole paper here. This advisor, Carlos Mestre, in UC Washington, they have developed many methods in the past. This paper explains everything about gradient boosting, and I highly recommend it. If you're serious in machine learning and serious in gradient boosting, you should read this paper. It was written last year, right? And there's these explanations and so on. So this is the actual algorithm. The math is not trivial, right? It's some kind of Taylor expansion of the loss function, and you can optimize it. And you make additive, like you add new trees, and every new tree that you add is supposed to fix whatever was wrong with all the previous trees. And it's a simple method, and the good news is if your loss function is any function you have as a function of actual and predicted, any loss function, as long as you have a gradient.
Twice differential loss function.
Yes. Right? As long as you have a gradient and a Hessian, you're fine. And that gradient and Hessian should be well behaved. So it means it's twice differentiable loss function. So it should be smooth. It should be something that happens in nature, let's say. It shouldn't be like a function that says if my actual is a real number but not integer or something like no weird crap. It should be just some smooth distribution. Okay? There's like mathematicians who would get that joke. Dirichlet function, something is not good. Basically, there's split finding math and all that stuff. This has been studied for years. It's a smart thing. You can cut up your data by columns and rows. And there's also a Microsoft implementation called Light GBM that does something slightly different, where they go down the tree and they pick the best leaf to split and go down that way. It doesn't have to go down layer by layer. It's kind of a slightly different search algorithm in the tree splitting. And XGBoost now also has that mode implemented. So it's a very generic algorithm, and we actually have all these features now in H2O as well. So we're very happy about that. But now let's actually run some stuff. So this is my server. And these are the CPUs on the left here, 40 cores and 2 GPUs. So the GPU is busy right now displaying this remote X, I think, of showing this bar here. That alone makes this GPU a little busy. Not sure why it's that busy, but nothing else should be running. So this is the script that's in this H2AI/perf/XGBoost directory that I showed earlier. But you can do that at home yourself. Everything is public. And here are the packages you need to install. So either you download XGBoost 2.7 or 3.5. That's the XGBoost Python module that has GPU support. And this only works for Linux and needs CUDA 8 on your box. So you have to have a modern box, basically, if you want to do GPU stuff. So now let's run this. Okay, imported everything. And if you want to run it yourself, you have to type maybe perf in the search bar on GitHub to find it. You have so many repositories. PERF. So let's run it on the Santander dataset, okay? Santander Kaggle is a small data set. Santander is a bank in Spain, and they had this Kaggle challenge where you have to predict something from some columns, but it's like 300 columns, and you have to predict whether the customer is happy or not, or whether it needs more work to like make them happy. Oops. So there's an if true here at the top. If set that to false, then it takes the other data set. There's another one that's called airlines. You've seen us present that before, I'm sure. The airline data set is all domestic flights in the US for the last 25 years or so. And this data set is 5% of it, so it's a smaller version of it, and we take another subset of it. So the limitation of the GPU algorithm right now in XGBoost is that the data has to fit on the GPU, all the data. It's not smart about paging it in and out. It doesn't use unified memory, if you know what that is. It doesn't like pretend to be just a main memory. It happens to be faster and it's on the GPU. It doesn't do any of these tricks. It's like a supercomputing code that says, put it in and then I'll do what I want to do with it. But it has to fit. Later versions might be optimized differently. So what we did also when we imported the data set, we said out of the 70,000 rows or so, how many you want to use for training. The rest would be used for testing. You know, I have a holdout set. We don't do any early stopping. We just basically build 200 trees with a reasonably small learning rate, and that's 8. That can be all the way down to 15, but no more right now, because that would require some type to be different to handle the number of nodes that you would get. So it would be more than 16 bit.
What
Yes?
is 16 bits?
It's just some memory savings in the XGBoost implementation. Like if you want to,
Single precision?
no, 16 bit is half precision, right? So it's basically saying 65,000 nodes in the tree. But if you wanted to have 30, more than that, like 4 billion nodes in the tree, then you would use a 32-bit number to index the nodes. It can be done. You would have to recompile it yourself and changing the type def, I would assume.
So it's basically done that way because it uses too much memory.
Yes.
If you were to build a tree that was depth, if you were to build a tree that was depth 40 or something like that, because the numbers of nodes are exponentially increasing, so you multiply by 2 every time, so you get some ridiculous memory usage if you have a statically allocated tree at depth 40.
Yeah, another reason is that he's currently allocating the whole tree at once, even though it might not go that deep. So if you know that it's only 6 or 8, you know it's going to max out most likely. But if you have, like, say, I have an unlimited, go to 100 or something, you actually will allocate 100, and that will kill
That's
you.
why you upper limit of 50.
Yes, that's why it's like safe.
Some stuff is more difficult to implement on the GPU, unfortunately. So that's just a constraint that we have to live with.
The hardware constraint. It's not bad, actually.
I think we can solve it later, but the programming is complicated, so it's just on a big list to do, things that we have to do.
So
the implementation.
This GPU, how much memory is there?
This GPU is a 1080 Ti, so it's 11 gigabytes.
So it's like K40, K80.
It's something like that. It's like a P100 mini version, basically. It doesn't have 16 gigs.
If you have multiple GPUs, can you make use of that other memory?
Not at
In
once.
about 3 months, I hope to release our multi-GPU implementation. And once we have that, basically you'll be able to split up the data set and you'll have a portion of the data set residing on each GPU. So if I have 8, what's the NVIDIA box, the DGX1?
Yes.
So what's the total memory of that?
The DGX1 has 8 cards that have each 16 gigabytes, so you would have 128 data
So you
set
have
size. Basically.
28. Yep. So you can fit some pretty large data sets once we get to that point. So.
The overhead of this histogram model is not so bad, so maybe even 100 gig of data you can fit, or even more. So it's really
able to fit some pretty big data sets on even. So we just released a new GPU algorithm which is very memory efficient. The old one, which wasn't, we were able to do. We were able to do 10 million rows or something on the hex data set, 10 million rows and 30 features on this Titan X card with 12 gigs, so you can process some fairly large data sets. So it's very good for single machine situations.
Did you try to split it so like in portions that fit each GPU, and then you just have some ensemble learning after that? on the top of that. I mean, you can just split like 8 gigs in 8 gigs chunks, so you train separate models, right? So you have several models trained on separate GPUs, and then learn some ensemble.
Yes, that works very well actually, especially if you bag the 8 gigabytes of data or 10 gigabytes of data from the original distribution with replacement, right? So, because it's relatively small samples. So yes, correct. That would be a good use of the DGX one before we have the distributed version of it.
So we can start the output of the fail, like the rhythm, the EWA, the HMS, right? So they over cell or over cookie how you start this kind of problem.
You were asking about a domain-specific use of the gradient boosting algorithm?
Yeah, usually some airline over cell, right?
So this airline data set, the response column would be like whether the flight is delayed or something. So you have to have labels in the data set, right? We're not predicting is the tickets, like what's the capacity planning of a United Airlines or something, whether you need to pick somebody's face in or not. I proposed to them to like, you can do churn prediction now. So yeah, I mean, data science is still the same, right? This doesn't solve data science for you. That's our next gen product. Hopefully addresses some of those questions, but you still have to have a supervised problem with good labels. And if you have good labels, then your feature engineering can be better or worse. And if you have deep learning that figures it all out for yourself, then all good, right? But usually that's not quite the case for time series and all that. It's not easy to come up with the super complicated group by aggregations per user, per store, moving window over 2 weeks or 4 weeks. The LSTM is not going to figure that out for you. So it's easier to make those features yourself and then give it to a gradient boosting method, especially if you have a DGX at hand, right?
You said you weren't stopping early with the script.
Yes.
Is that just for simplicity?
Yes, for simplicity. So what you never should do is just train with training and say good luck. And I guess 500 trees. That's never good, right? You should always use a validation set that you pass in and say use 10,000 trees, but stop once it starts overfitting. Maybe get the best point.
So I'm very curious. The overfitting problem is because many these kind of data patterns doesn't fit with the same data set in real time.
I'm not sure this data set is used today. Like this is old data, right? Any data that's outdated by 2 years is useless usually. This is just historic flights, and you can see that San Francisco is usually busy or something, and you see that there's a delay. If you're in San Francisco and you want to fly to Washington, then usually you're late or something. And it's kind of.
So you all data processing can only predict how many people are the night can put in your data set to predict.
So basically, this model can learn from the existing data and just memorizes what's typically, like it's a compression, it's a data compression method, right? You basically get the big picture. When somebody asks you, hey, is San Francisco late or not? You say yes, because it's usually late. It's kind of what happens. And the more trees you have and the deeper they go, they say, well, wait a second, what time are you talking about? Or what airline are you talking about? And then once you say that, then you say, well, okay, this airline is late, but this airline is not, right? So it's just a kind of a different compression with more and more capacity. And the big model has more capacity. And currently we're limited in the capacity of the models. But you can build, I think you can build lots of trees, right? The final trees are stored on the CPU, right? You're just making them one after another on GPU and pushing back to the CPU. So your main memory, as long as it can hold all the 10 million trees, let's say, you can build 10 million trees even on GPU. So depth 15 is just fine, because usually you'll get the interactions by the time you reach the 10,000th tree.
So you're running with your validation set on the main CPU. So you need to detect when your error on validation set goes up. So you have to run it on the
So the issue with the validation scoring right now is that it will slow down this benchmark because it goes to the CPU to score. It's not using the GPU. The GPU is used to do the histogramming and the splitting and all that, but not for scoring. So we decided to just do the training to a given number of trees. And you could then, in reality, you would probably score every 100 trees and not every single tree, let's say, because it's kind of wasteful.
Our new histogram GPU implementation was. Our new implementation ended up being so fast that the validation set, the evaluation of the validation set ended up costing more time than building the actual model itself. So we ended up in this position where we've optimized everything so much that we need to go back into the algorithm and optimize the things that used to be fast but are now slow.
All right, so I parsed that file in 2.5 seconds. I'm going to split it by the first million, or what was it, 70, 60,000 something? Here, 60,000. So let's do this mouse. 60,000 training rows. You're dropping the ID, depth 200 trees, okay? And all I'm doing is some drop and stuff in pandas. That's all standard work. So now we have 2 files. One is 170 megs, the other one is 45 megs. So we're training on a 170 megabyte data set. It's not big, but it's nice Kaggle-like style, 370 columns with 1,000 rows. And let's look at the CPU. CPU has 40 cores. Here it's a dual socket Xeon, okay? So I have a two Xeon system with 10 cores each, physical cores. And so you can see the memory, 256 gigabytes and 2 1080 Ti's. So it's a fairly okay box, but nothing to brag about. These are the GPUs, and now here's the method that we write. So the method says, make some strings here and print them out. Tell me what I'm running. Then make me a D matrix. That's what you need to make for XGBoost. It's just a pre-processing of the data. Basically makes a sparse data structure with sorted columns so that you can easily split. I'm not sure if it has the sort for a histogram one or not. It might be smart about it or not. I haven't looked at the D matrix code. And then we say train, and we measure the time for each of these pieces, and then we say predict. And predict is on the test set. And then we compute the AOC using some scikit-learn ROC computation. The AOC is the area under the curve under the precision recall, actually a receiver operations call, which is like true positive, what is it? Yeah, it's true positive and false positive rate. And true goes up, false goes to the right. So ideally you want to be on the top left corner, basically, where you get everything right and nothing wrong. And the curve is usually like a little smooth, not sharp, right? So you have some error somewhere, but you have to make a compromise. If you say everybody is yes and nobody is no, let's say, then you get all the yeses, but you get all the no's wrong. If you say no to everybody, then you get none of the yeses right also. So you have this compromise. So you'll find the threshold. But the area under the curve gives you the quality of the model. And the best number is a 1. The integral under the square basically is 1. But usually you don't get there. All right. So make some arrays, and I'm going to fill those up with every model that I build. I push some numbers in, later we can plot them all. So this is the first model. Let's go. So this model is building on CPUs, as you can see at the top, and I'm doing an exact method. So this exact method is basically the most numerically accurate gradient boosting method. So it says for every, let's say, age or income, whatever my simple example data sets, I'm going to ask every single income that I found in the whole data set, should I split at that value or not, right? And there could be 60,000 rows, and everybody has a different income, so I need to decide between 60,000 different numbers, where should I split, if I were to split that income. And then I look at what's the, for every point I split, what's the improvement of my loss function. The loss function would be, for example, log loss. where I say if I predict a 0 for a 0, it's perfect, no loss. If I predict a 1 for a 1, it's also perfect, obviously. If I predict a 0 for a 1, my loss is really bad. It's like 31 or something. Basically, it would be infinity, but we're not quite going that far because it can't penalize too much, so we cut it off at some point. But it's going up as fast as the logarithm goes down between 0 and 1. You know, the logarithm is something that comes from minus infinity and comes up, right? The way it goes down into that hole is pretty steep. That's the loss that gets worse and worse as we get closer to 0, when you should have predicted a 1, where the logarithm is 0. So that would be perfect, and that's bad. And so the cost is pretty bad. And that is a good loss function. And you could compute that. And you could then say, well, where should I split? What would be the improvement to my loss function? And if I split at this age, what do I get? And then we say, well, age maybe overall doesn't really help that much. Maybe it's better to split it from income or some zip code or something, and you find the best column. So for every leaf in the tree, you have to ask every column. You have to ask for every column, every value for that column in the entire data set. Where should I be split? And then you decide to pick the very best across all of those. It's very expensive, but that's what gradient boosting does. And you see here it's finished. It took 20 seconds to train, got an AOC of 84, and prediction was really fast. And even the data creation at the beginning was fast, 0.6 seconds. Now we're doing the same with an approximate method. The approximate method is doing histograms, so not every income in the data set, but some incomes. And at every split in the tree, as you go down, you only have some incomes left because you split off the rich guys first, right? So then you make a new histogram for like minimum to only 50,000 or something. And you adapt those histograms. So now it's still running. You can see all the CPUs are busy. Hopefully it's a little faster than 20 seconds because we're not doing the exact method. But this is some extra work actually to make all these histograms. So maybe memory-wise it wasn't that efficient because all these threads were competing in filling this histogram up and all that. So there's some computational overhead where it might not actually make sense to do the approximate method. So try all methods basically and see which one's is fastest for you. It gets to the same AOC of 84, so that's good. Now we're doing the histogram method. That means the histograms are not dynamic anymore, but it's fixed. So at the very top of the tree, you say, what incomes do I have? Okay, these incomes. Now I do 256 bins by default, and I find them the location of those bins by quantiles. So basically a 0.5% or something, right, for 200. So every 0.5% of filling the population I cut. So it's not just every $1,000, but it's by occurrence. So every cut should have, every bucket should have even number of people in it. So if there's equal many millionaires as people with only 1,000 income, that will be the buckets. To make it like a better distribution. But even that wasn't going to help much because in this case, there is an inefficient implementation, it seems, in XGBoost for multi-threading. So there's not that many bins, but all threads are competing to fill the same bins. Maybe there's some issue there. Now let's see what the GPU does.
So what you're saying is it blocks.
This is not using, sorry?
What you're saying is that it blocks, delays, and waits.
It's not blast called here, but it could be some multi-threading issue where
It's a block.
block, B-L-O-C-K, yes, correct, yes. Yeah. I'm not sure it's blocking. It might be just memory access limited. They're just computing. Everybody's trashing the cache lines. Where I say, hey, I want to write, and then you say, no, I was writing. Okay, destroy me, then you can have it. And then I say, no, I need it back. You need it back, and we go back and forth. And all we do is write one number, right?
I think their implementation is just. I think the algorithm implementation for the fastest algorithm is not that. It's parallelization by feature, which is not efficient when you have large numbers of threads. Interestingly, we found that if you have a 40-core Xeon machine and you compare it against a 4-core i7 or something like that, the i7 is faster. Yep.
What do you use for parallel multiplication? So like ETH Zurich or
With an XGBoost, we use OpenMP for everything.
the 4th generation? Which version of it?
I don't know. We're probably using GCC around 4.8 or 4.9 for most of our builds, so I'm not sure what the sort of standard version you get with it is. Yeah.
So the GPU one took 18 seconds. It was still not that much faster, but I think it's the fastest so far. And now we're going to look at the latest one he just wrote a week or two ago. You see the GPU is busy here, right? You saw the GPU here going up and down to 3 seconds. Also 84 AUC. So this is 5 times faster than the exact method and faster than all the other methods. So let's look at the frame, the summary frame. So these are the numbers, right? You can see that the GPU histogram one is 3.7, where everything else is 20 seconds and up. And that's giving the same AOC at the right side, up to like noise. You can run it again, it will be different. Most likely, or the seed is different, whatever. If you change the seed, it might get slightly different number. So this is only 60, it's evaluated on like 10,000 rows or something. So it's not significant. But the significant thing here is that the D matrix time is the same because it just made the matrix basically over and over again at the beginning, which is measured at 0.6 seconds every time, so that doesn't change. The scoring time doesn't change because it's single-threaded scoring on the CPU. The training time changes, but the validation time also, the AOC also doesn't change because it's not in the same model. So it's not guaranteed to be the same because the binning of the histograms changes the algorithm, right? But usually binning not too sharp is actually a good thing, otherwise you overfit. You don't want to say, oh, if your income is 67,221, then you're something, because it's just luck because that one guy did that in that data set. Right? So it's actually a good thing to do binning. That's what H2O does as well. And we can plot this. And this is the performance chart with time. So this is how good XGBoost is on GPUs, right? So I think there's some applause that we want here for Roy here. It's pretty good. So we've worked for years on GBMs, right? Tried every for loop, every atomic update, every cache operation, every memory line cache, this and that. And he comes along and just crushes all these numbers, basically, right? And that's, of course, also needed in the GPU, right? But knowing how to program on GPU is actually fairly difficult. It's not many people who know how to program a GPU efficiently. So we're glad to have him part of the community and help us write GPU algorithms and make those more efficient. And C++ basically is back in full force, and so is HPC, high performance computing. It was my former background, so I'm kind of glad that we can bring those two pieces together.
Second question.
Yes.
You have two GPUs with this type cut down roughly by half.
Yes, yes. Eventually it would.
We haven't finished that implementation yet, but the new implementation. Actually, in this case, actually you wouldn't. So that algorithm took 3 seconds to run, and that 3 seconds is mostly actually overhead. So it's going to take between 1 and 2 seconds to do some preparation on the CPU at the start, and then it's going to go. So, but if you have really, really huge amounts of data, yeah, we are hoping to get to halve the time with 2 GPUs.
But
yeah.
you would not see the CPU as a bottleneck at any point, right?
For validation, if you're doing a lot of validation, that can slow it down. So if I've got an 8 GB, 8 P100s in a box or something, and a slow CPU, the actual tree algorithm is going to be so fast, and the CPU is not going to be able to keep up with validation. And that's another thing on our to-do list. My basic recommendation is that if you're using one of these really, really fast algorithms, you might even consider using a very, very low shrinkage parameter or learning rate, doing more iterations. So people would commonly do something like 5,000 iterations of boosting to get a really good model, and check your validation every 5 iterations or 10 iterations, and see how that goes.
I would go as far as say every 200 or something, right? Do 5,000 trees every 200 score. But I think once he has we have the scoring on the GPU, then you will see no bottleneck other than the first second to create all this data stuff. But once it's running, basically it should be fast. So the communication between the GPUs is the histogram communication. H2O has done this for years, right? And we've been communicating on Hadoop clusters and all that, and even 10 gigabit links and so on. These cards are between PCI Express buses at the worst or best NVLink. NVLink is even faster, right? It's like memory bandwidth. It's really fast. Tens of gigabytes, if not hundreds of gigabytes a second. So there's no real time penalty to send over a few kilobytes of histogram numbers. That's going to be instant. So we expect it to be almost linear. I mean, more than good enough, let's say, to get to 8 GPUs. But the DGX will be a good machine for gradient boosting. You can fit 100 gig, and you can be pretty much instant training if you want. Yeah. Yes.
Can I train your models on GPU and use it in CPUs for inference?
Yes. Yes.
So referring one ETH path or one
eventually, good point. Eventually, after this multi-GPU implementation, there will be a multi-DGX implementation, if you want, or multi-node implementation in general, where each node can have multiple GPUs, and then they all work together. So you just have to shard your data, and then all the GPUs have to reduce the histograms, and then one worker has to decide, basically, okay, thanks, that was the split, now we need to compute the gradients. And I think that's still a bottleneck right now, but eventually that also could be moved over to the GPU, the gradient computation. But the partitioning of the data is already done on the GPUs. So the GPU figures out where to split and does the splitting if you want as well. The only thing that the CPU does right now is it says actual predicted, that's the gradient. And that math is done on the CPU. But you could make a CUDA kernel that computes the loss function and the gradient and the Hessian and so on for these different like binomial and multi-class and so on models and regression models and so on. You could do that math on the CUDA kernel too. So in theory, everything can be ported to the GPU. And there's even a collaboration between us and NVIDIA, and well, NVIDIA sponsored it basically, or started it, but it's really us and Continuum and MapD, and we're trying to make an in-GPU data frame. So the point is that you have data, you move it to the GPU once, then you munge it, however you do that, hopefully with Continuum MapD, maybe with H2O eventually, if we have a PyData table, but there's some way that we can munge the data on the GPU and then say, go build an algo on it, right? Where you don't even go to the CPU. So this whole D matrix could be created in the GPU, but somebody has to write all that code, right?
Because right now it's a drag.
Yes.
Right now it's just let it out.
Right now.
What did you think of the show?
GTC?
Yeah.
Oh, it was very inspiring. I liked it.
Yeah. Was there a lot of interesting new competition?
Not really. We were surprised not to see many people talk about machine learning. Most people talk about deep learning, right?
Strange.
Yes, correct. DGX uses 2 Xeon chips that each have 20 cores. So the top of the line, $5,000 chip each, so $10,000 of Xeon chips in the DGX. 512 gigs of RAM. NVLink between all 8 cards, every one card to all the others, and then of course the cards have 16 gigs of RAM times 8. And the ARM processor is used for their IoT devices, like whatever it's called, the Jetson TX2 or something. They have a TK2, but they have an ARM chip plus a GPU. Yes, there's other spinning multiprocessors, not just NVIDIA, if that's what you're saying. There's also Google's TPU and so on. The whole market is warming up to this idea of making hardware that's good for AI. But most of them are optimizing for deep learning because it's such a promising technique. But still, experts are saying deep learning will only take half of the market of analytics, if you want, or model building. Not everything, right? Not everybody will only build deep learning models. If you have this Santander data set, you might not get away with a Keras TensorFlow model, for example, if you want to win Kaggle. Might just not be good enough. Because doing the split at income 70,000 is much easier with one split than to have a neuron combination, make a rectifier that cuts off at that level and so on, right? It's just more work, but I mean, it's doable. It's just a question of how much complexity you throw at it.
I mean, it's not, my question is not about specifically this XGBoost. I wanted to ask about if you're planning to allow to build flexible deep learning models with H2O instead of just specifying, 200 by 200 by 300 by
Yes,
300.
we actually have that now. We have deep learning, TensorFlow, and MXNet. And for TensorFlow and MXNet, you can make your own graph. So you can use Keras, make your 2 GPU deep learning model with your own TensorFlow graph. Like you can build anything in TensorFlow you want, give it to H2O as a protocol file. You literally give the path to the file, and you say run. And then H2O will tell TensorFlow to run it, and will feed it our data in mini batches. So we have a full integration of GPU deep learning, multi-GPU. So you could even run on a DGX TensorFlow from H2O and see the whole convergence and flow, get the model back into R, get a mojo out. You can also get a mojo for this model, by the way. So I can go real quick, show you that. So first I need to run H2O, of course. I haven't done this yet. So let's start H2O. So now I'm launching an H2O instance on the same server, because we imported a Python module at the very beginning that had this in it. So this H2O has XGBoost in it, in the jar file, okay, with GPU support. And now I define this method. It's a little bigger. This method says, okay, print me again what I'm doing, and then make me an H2O XGBoost estimator, and then train it on some columns, okay? And there's a training frame. It's the same way as H2O, GLM, GVM, deep learning, DeepWater, random forest, whatever it is. It's all the same. K-means. And you can predict, and you can also bring the predictions back into Python on my laptop. Well, actually, this is the notebook that's running on my workstation, but it gets it back from the server to Python. The Python normally doesn't run anything in the H2O world, right? Here earlier, it was actually running XGBoost from Python. But when we run Python normally in H2O, we don't actually run anything in Python. We just make strings that we send to the backend that's Java. So the Java system runs the algorithms. And Python was just a command and control center. But XGBoost does run from this in the same box as where its Python process is running, right? So that's a difference. So H2O is more geared for like enterprise deployments, let's say, where you have a 10-node Hadoop cluster or Spark cluster, and you want to control it from your Jupyter notebook, and you tell the 10-node cluster to suck in this 100 gigabyte data set from Hadoop, for example, and then you run on that 10-node cluster. And your Python script is just controlling that.
You combine the sparkling water and deep water and reduce it as a single data.
That's coming up, yes. But I'm not sure if Michal is here. So sparkling water and the H2O deep water, both are using just the Java underneath, right? It's not much. It should be like one page of code at most to make the wrapper different. So it wouldn't be much work. I think the next release 3.12 will have XGBoost in it. And then the release after that will have DeepWater in it, in the official release. But you need to have this plug-in mechanism where you have these extra jars with the native code. That's where it needs C++, right? Because you can't just say, here's a jar, run it on your Mac. It's not going to work. So we have to make this plug-in mechanism. And for XGBoost, that's easier to do than for DeepWater, because DeepWater has 3 different backends, Cafe, TensorFlow, MXNet, and so on. And to bring it into sparkling water from the Spark side, that's another extra step.
So you
We have our own for the standard fully connected neural nets, but not for convolutional neural nets and more complicated like LSTMs and so on. For that, we use the GPU backends. But those can also use CPUs only. Like you could run TensorFlow on a CPU, right? I'm not saying it has to be GPUs, but we're using TensorFlow, Caffe, and MXNet as a backend to which we can provide their own graph definition files. So you can make any graph in Keras or in raw TensorFlow, even multi-GPU graphs that do image augmentation on the fly, for example, and can pass this graph to our Java engine that then passes it on to C++. And the benefit you get is that you can do this all from one framework. You can do it from Flow, from R to Python, from Scala. You can do it in a way that's deployable. So when you like your model, you can say deploy, basically. You get that whole thing deployed as a Java thing that you can plug into your enterprise applications, right? Because all the bytes that go to the C++ engine are wrapped into this Java deployment package. So we basically take care of all the deployment issues, and there's also AutoML now where you can do automatic machine learning where it hyper optimizes for you and picks the right model. So you can say I have 12 hours of time, go, and then tomorrow you'll come back and you get like the best model that was found in 12 hours. We have all these things now in H2O3. So that's one of the benefits of H2O. It gives you a little bit more than just a raw engine. XGBoost is more of a raw engine. So this is the logic to train an XGBoost model in H2O. So all I'm saying is XGBoost estimator. And then we reset these arrays. Actually, we make new ones. And now let's run the exact CPU version that took something like, I forgot how long it took earlier. What was the time for the long one?
40 seconds.
CPU exact, that was like 20 or 30 seconds for this kind of stuff. So let's see if we get something between 20 and 40 for CPU and then 20 down to 4 on the GPU, okay? So H2O, by the way, can take the H2O arguments for GBM, or it can take the XGBoost arguments. So the name could be learning rate, or it can be eta. So XGBoost has different convention than H2O. If you have tried it yourself, you know you have to like remember the names and all that. We accept both, so that's kind of convenient. If you don't remember it, you just try it. Okay, so this was the exact CPU version of XGBoost. This took 14 seconds. So it's actually a little faster, it looks like. There could be some fluctuation too, like every time you run it might be slightly different because of the, whatever, the cache.
So the in which flow is that? H2O.
Yes, yes. You can give an H2O frame with categoricals in it and missing values, everything, and then just say go to XGBoost and run, and it will actually work because we do the one-hot encoding, for example. So the default is one-hot encoding, but there's also label encoding, eigen encoding, binary encoding, sort by response encoding. Like there's all kinds of different things. So you can actually sort your categoricals by response, and when you then line it up, and you have more than thousands of, like let's say for, actually I'm not sure it helps for XGBoost because it doesn't have, no it does. I think it will, okay, what it does is like a label encoding. So it will say, you have cat, dog, mouse, right? And their responses are like growing linearly. And you're supposed to split somewhere. If they're ordered and you split somewhere in the middle, then chances are good that you found a good split because the low guys are left, the big guys are right.
Multi-class classification?
No, just for single class
Okay.
or regression, doesn't matter. So if you want to separate your animals by height and you sort them by height and you say, I need to cut here, right? That's a good idea. It's better than to randomly shuffle them and say, I cut here, because then left and right would be even, basically. So sorting by response is a good idea if you then turn it into numericals, because that's what XGBoost wants, all numbers. And then it can split. But there's a danger of overfitting, of course, because if you only have one snake that's like really big and you put it on the right side, that's not necessarily the best thing. So it shouldn't be just sorted by size. It should be sorted by weighted size or something like that. You should be more smart, but I'm not doing that. We just sort by response. That's one of the many encoding schemes, but that's one of the benefits of H2O. It basically does this for you with different schemes to choose from. You don't need to do that feature engineering yourself.
So the matrices, so you don't need to
Yes. 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 So my job now was to write a D matrix creator from an H2O frame, and I had to go over and make a sparse D matrix or a dense D matrix from an H2O frame and do this one-hot encoding on the fly and all that, and fill that matrix. One issue is right now that the D matrix constructor in Java only takes a float array in Java. As you know, these arrays can only be 32-bit addressed, so not 64-bit, which means it cannot be too big. If it's more than a few gigabytes of data, it won't actually work. So we have to make another constructor for D matrices from Java where you pass a list or an array of arrays to have blocked data, so you can fill up 100 gig data structures. So it doesn't exist yet. So I will have to make a pull request to XGBoost to add this Java constructor for big data. But usually, actually what we're doing is multi-node as well. We'll have a multi-node version of XGBoost. So for those of you who want to run your own XGBoost in a distributed case, you will need to know how to launch it on in Spark and so on. But later the H2O will just automate it for you. You don't need to worry about it. Basically, we can just launch it in H2O because we already do the distribution. All right, so this one was 10 seconds. This was the approximate method. And as you can see, it's running nicely, and I can go to this box and ask H2O, hey, did you build a model or not? You can look at the logs, but I don't think it's much. It used 200 megabytes here.
Could you run NVIDIA SMI just to see how it?
Yes. This is NVIDIA SMI, by the way. So this guy here is the usage, but not memory. It's just the CPU usage. So Python itself uses 173 megabytes. And that's what it was saying here roughly. This was allocated 200. So we now can run the last one, the histogram method. This was the CPU histogram that again wasn't that good because it was not optimized for that many cores. I have a too good a system, I guess. Now this is the exact GPU method, which was 18 seconds earlier. It's actually faster now from H2O. I guess that's a fluctuation. We can try it again later to see why. But and now we're doing the histogram method on the GPU. Note that I don't provide the updater option in H2O. So I tried to be smart and just say backend CPU or GPU, and then the rest is automatic kind of. It will by default use this new fast method. But if you set the tree method to exact or hist, then that is the same argument that also toggles the hist or exact method on the CPU. So it's the same back and forth. You just have another backend CPU, GPU. But I guess the future implementation of XGBoost might have another set of actual parameters, at which point they might adjust. So also 4 seconds to train. Takes about a half second longer because it also has to make a D matrix. The other one was just counting the training time alone, not the D matrix. So now I want to show you here in H2O, you can go now to model and say list all models. But as you can see, there's other stuff you can build. There's DeepWater, it has TensorFlow in it, there's gradient boosting and all these other models. This is the XGBoost. So here is XGBoost. You can say build model on this training frame, train. And you can say I want to predict, say, this variable here, target. I want to ignore ID. Okay, 53 step 5, it's fine. Everything here is, all the parameters are there. Call sample by tree, minimum split improvement. That's an H2O argument that the XGBoost also has. You can provide whether you want exact approximate or histogram. And with the default, I guess I can do hist to show you that it's actually what's happening. We have loss guide and depth-wise. Loss guide actually gives you the light GBM combined with the hist. So this would give you a light GBM, and this will give you the Rory's algorithm. But light GBM doesn't yet have GPU implementation, so you have to know that. They do, but not XGBoost, yes. So when I say light GBM, I mean their algorithm, not their actual implementation. And you can also say whether you want dense or sparse D matrix. In case you have sparse data, that can save you a little bit of memory so that the float array that gets passed to Java of XGBoost fits. Because if you have 2 gigabytes and it's all sparse, then please don't use dense because it might blow out that float array. But if you know it's sparse, then it can be smaller if you make it sparse. But it's auto-detecting that, so you shouldn't have to worry. This bin number is important. If you do more bins, you get a sharper resolution, so it might make your model better, it might not. It depends on whether it's overfitting or not. And all the other arguments are there. You can do GB linear, Dart, all these other booster methods that XGBoost has are all supported. And now the backend has GPU or CPU, and I will leave it at auto because it will detect the GPU. So now let's see if we can actually make this use the GPU here as well. Oh, it's already done. Yep, done. Could barely see it. So let's make it a little deeper and a little more trees. Let's make it depth, let's say 13. And let's build 500 trees. So now you see the GPU getting used, right? And this will take much longer on a CPU. So we have a Kaggle master in house who says he likes depth 25 for GBMs. So, but others are saying 15 is fine. So I would say 15 is fine as well.
It's like non-linear.
Non-linear interactions. Yes.
Yes. You don't have 25 depths.
But it's not just the interaction. It can also be self-interaction. You can say age this, and then age this, and then age this, and then age this. So one tree can chop up the age more as well. It doesn't have to be interactions, right? So it gives you more resolution.
I think it always depends on your data set. But for many data sets, we find people more than 10 trees sometimes gets better results. But you basically have to do cross-validation and work it out. So in a lot of cases, you can get better results, better accuracy by using more than 10 trees, but not by much.
So this is the convergence plot, and you can look at this point, and you can see here the this was a RMSE. So this was the original data set where I didn't convert the response to a factor yet. So I just picked a frame in H2O, and I did take the one that was parsed from a file, but I didn't convert the response to a categorical. So this became a regression model because it was a not factor response. So if I had to take the other frame here, most likely, that is this Python 2 thing. This guy would have had a response that was categorical. So you have to go to the end of the data set here. You don't have a better way to get there, unfortunately, yet. But
You're gonna have a button.
we might not ever, because we're now, who knows, maybe there will be somebody who volunteers that. If you have that many columns, yes. Even this one doesn't have enums yet. So even this wasn't the right data set. So unfortunately, there's not an easy way to do it in Flow. You just have to look at it. But you can do it in Python, right? You know the handle in Python because you assigned it to something. Usually you would do this kind of scripting in Python. But the point is that you can do now from H2O, you can look at the models that were built. So these are the models built from Python earlier, right? And I can look at this one, for example, and I can see that this was the model that had GPU histogram. That was Roy's algorithm. I only scored once at the end after 200 trees. It took 3.1 seconds to actually train. That's in line with the time it took on the XGBoost algorithm. The other preset time was maybe outside of the actual algorithm. It was the time it took to launch the job or something else. You can see the AOC curve. So this is what XGBoost doesn't give you, right? This extra stuff. And you can also like ask where is the maximal F0.1 score, some precision recall hybrid. You can get the feature importances, everything visually. You can get the gains lift table. You can look at the lift in the top 2 deciles. You have a lift of 1.3 in this bucket, or total lift of 4. 4 times better at detecting the yeses versus guessing the average. All this kind of stuff. So it's kind of cool to have it now integrated. And you can also deploy this package, this model here. It gives you this model deployment package. And when you open it, it has the bytes in it that goes to C++. It has like a list of domain names. 01 was the response. It's the only categorical thing. Oh, sorry. There is some more details, like some JSON file that explained what was in it. You wanted to inspect it some more. There's a README, and there's an ini file that says like what the parameters were and so on. So this is kind of a nice self-contained deployment package. And we have examples that show you what to do with this zip file, how you can deploy this model in a production environment. But again, it's only scoring on CPUs, right? And then when you want to run H2O GBM, the old school H2O GBM, that's using all the cores. But it's not 4 seconds, right? It's slower. Because this is a wide data set with 400 columns, 60,000 rows, but each column has to do some work, and it's just not as fast as a GPU. It's just the memory bandwidth just can't cope with it. But it's still in the order of the time of 20 seconds or so, comparable to XGBoost. And it does handle all the categoricals for you and all that. So it's not bad, but it's no longer the fastest, basically. And this is for a data set. Oops. Yeah, here you get the 4, 6, 10, and so on, and then at some point H2O shows up. So H2O is not the fastest, for sure, on this data set.
So it's roughly the same AOC.
Yeah, the AOCs are roughly the same for everybody. So you can look H2O, actually it's the worst here. But this is on validation after no early stopping. So maybe H2O overfits already after this many trees. So it's not fair to say, what's your AOC at 200 trees? You should really do a tuning run where you early stop based on the validation set. So it's not quite fair to compare validation AOCs if you didn't actually tune for it, but just ran with one blind guess of different algorithms. Now what you can do is you can change this data set to become the airline data by changing that back to false. And I can actually just run the whole script from scratch. And while it's running, let's try to go to this Nimbix thing. This is the DGX1. I'll try again to get in. So literally you can ask for a DGX1 here. It's pretty cool. It's only $30 an hour. So it's queued. That's what I saw earlier for like 2 hours. So I tried to launch one. I would have left it running just to show you, but I didn't get to it. So this seems to be a scarce resource now. So let's keep this in mind. If it ever shows up, we can do a live demo. But in the meantime, we're running these on the airline data set. So the airline data set is here. You see 3 million rows, only 12 columns. So it's just long and skinny, and you just have to walk these columns of what day, what year, and so on, what flight number, what origin. They're just integers telling you which airport it is. It's already mapped to enums, basically, categorical. So there's an integer encoding of the strings. Each string has a number associated. So again, we're running all the stuff. You see the CPUs are not particularly busy, but that's depending on which histogram algorithm is running. So this is still the very first algorithm, so it's taking a while. maybe I can just show you the results on GitHub. So this was what I ran earlier, the results for airline data, where this was set to false. So we did run this one. Yeah, 3,300,000 megabytes of data on the Xeon with the two 1080 Ti's, okay? And we run blah, 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 all this stuff. Let's look at the charts. Here we go. So here even more, the tiny took the exact CPU algorithm, the one that you would want to run normally if you don't know what you're doing, and by default it actually would switch to the approximate method. If you just run XGBoost by default, it would say, I don't need to do exact, I can do the approximate one. But unfortunately it takes the same time. So it would be 200 seconds to run XGBoost on the CPU. Now it's 10. 20x speed up, right? The same accuracy. So that's pretty significant. And now, of course, you could say, well, it's not quite the same. It's like a little bit different. So, okay, sure. You can use a different number of bins. You can change the seed, see if it's significant or not. But the more bins you use, the more it should approach the exact method. But this is significant. This is game-changing in my view. 20x speed up over XGBoost is pretty significant. It's on one GPU. And I have actually two on this box. I put 40x. This point is kind of pointless to do anything else. Of course, it only works for small data, but I'm almost willing to do the valuing approach you said to get to that small data and then do statistics because it's doable, right? People have been doing it, especially if you have imbalanced data. You can down and up sample, you can make your data sets balanced and then do the prior adjustment as you go back to making probabilities and all that. So you can actually work with that statistics you have much better than throwing the whole thing in Hadoop and hoping for the best, basically. And here we do the same on the H2O side, all these algos. Same story. This time is taking the time for training plus the matrix creation. So we didn't add that to the upper clock. If you add it all together, we get something like 30 seconds in H2O. So it's still getting to 230 in H2O. If you run it again, maybe it's 20, who knows. But basically, that's what I wanted you to take away from here. You should try this. It's open source. It's available. You can download it. You can try it. If you don't have a GPU, you should buy one. I recommend the 1080 Ti, 11 gigs of RAM.
They're 3K now? What are they?
700.
Oh, good. I blinked.
I bought 2 of those for my home PC, and it gives me a reason to implement or help with the distributed algorithm. So the GLM we used earlier in this music video that was a different algorithm was also using both GPUs. So from now on, every algorithm we write will be on GPUs, basically.
What kind of PC you have? So you have 2 slots.
I have actually three slots. Most motherboards have 3 slots for graphic cards.
Oh. So you can just kind of.
It's just $200 motherboard or something. It's nothing special. Yeah.
You need the white.
You need the big tower, basically. Yeah.
You need the white.
Yes, you need the long one. Yeah, because the cards are double.
I have a question. With more and more libraries involved, binary JNI pieces, are you planning to have a Docker to ease the deployments?
We actually have a Docker image already.
Is it going to be part of NVIDIA Docker? Because NVIDIA has a Docker itself.
So the service you showed, the MC chart service, that was the 1080 Ti that you ran, or?
Yeah, it's still queued. It's not done yet. That was Nimbix.
Okay.
Nimbix is you can log it, you can make an account there and pay $30 an hour. Basically, you get a DGX.
DGX had P100s on it. All 8 P100s on a single train.
So I'm not sure how we can share Docker. Is anybody here that knows from H2O where our Docker instructions are? It might be. if it's not evident where it is, then you should make it evident. You should post it somewhere. Is it in DeepWater? Okay. So you go to H2O AI, GitHub, and then DeepWater. And then in DeepWater is a README, and that will say, here's like some pre-release downloads, blah, blah, blah. You can download these things, the egg files for TensorFlow and all that. But one of those packages, actually, this H2O DeepWater pip module here, this is actually the one that also has XGBoost in it. But then there's a Docker one too. So there's an AWS image. This does not have XGBoost yet, but this is the Docker image. So we'll update the AMI soon, but the Docker ones, this is how you do it. So NVIDIA Docker,
So on Amazon,
and then you do Docker run.
On Amazon, it will be easy because you're gonna have just named image, right?
Yes, and on Amazon you can get an image that has NV Docker from pre-installed, everything, CUDA on it, or if you don't, I mean, whatever it needs, the CUDA is really on inside the NV Docker. And all you get is a port exposed on which you can open Flow, for example, that then has XGBoost.
One more question. What parameters to XGBoost? GVM has a way to set up some dropout, right? You scroll quickly. I didn't see if it still support dropout.
I do subsampling of rows and column sampling for columns, okay. Yes. And the column sampling is done by tree. So for every tree, you pick 90% of columns, and that's it. But you could also change it per each split. Every leaf has a different 90%, for example.
So it's basically like
all sampled by level or something.
There is actually another dropout mode in XGBoost.
There is another sort of more experimental dropout mode in XGBoost that actually drops out trees. So as you go through, let's say I've got 1,000 trees built already. When we evaluate the model, we randomly ignore some of the trees. So.
Yeah, we added some stochasticity in H2O GBM as well, where you can have like random split points, something like extremely randomized trees, and then also there's another one that does like a random noise in the leaf node predictions. So if you say, okay, this is a node, my average income is 75,000, I can say, well, no, make it 76,000 just by luck, like randomly just throw a Gaussian noise distribution around it and change the leaf node prediction. So we have this stuff too, right? But we haven't proven that it's useful. It's just another regularization technique. We can throw in some blinding the model, basically. But I prefer to smooth the data and then make a sharp model more than to make take good data, let's say, and then make a bad model, right? So it's usually a better idea to make the data the way you want and then fit something easy, even GLM, if you understand what you're doing, better than having the data with all the noise in it and then fitting something bad to it. But both approaches seem to work. Okay. So is there any questions? We still have Rory here, and we're running the script, so by the end of this next 5 minutes or so, we'll probably have live results, but I don't expect them to be that different from what I showed you earlier. Yeah, it's already done.
So your plugin or your driver, is it written to put an M, or what is it written?
He asked me which language it's written.
Well, what interface it is written to? Is it CUDA-NN or it's
CUDA-NN? That's neural network library, so that doesn't really help us. Basically, the whole implementation is written from scratch in CUDA. To find this on XGBoost, you can just Google XGBoost GPU and you'll find a bunch of stuff. It's kind of difficult to build on your own if you want to play with this and try it. I actually recommend that you use the pre-built Python wheels that Arno should have provided at the top of the script.
Yes.
That should work for a Linux system.
That's your code. All this stuff. CUDA.
So I look too carefully at my code.
There's all this stuff, right? GPU, scans, reduce. So yeah, it's not easy to beat his code. I think the point was that somebody tried actually to beat his exact GPU code, and it worked in some cases, but not in others. But then he showed up with a better version of the algo with the histograms and beat it by 5x, right? So premature optimization is not good. Like, think about the algo first. And H2O and XGBoost have done the histogram first. So that was the natural evolution. And also, histogramming helps with distributing, right? You can make your local histograms, and then you all aggregate them and have the final histogram that's a sum of all the other histograms. And that is the only way really to parallelize GBMs as far as we know. And that will work on a DGX. That's really all you need for the next few years, right? Is to get a DGX to GBMs really well. So I think it's a good idea to like move forward fast and not try too deep to optimize.
Do you see a lot of promise for feathers?
We use it sometimes because it helps between R and Python. Feather is kind of a binary file format that is using arrow memory layout and serializes it with protobuf-like structures, flat files. And if you have a data frame in Python, you can do a feather write, and then in R you can read it, and you can go into the data table, for example, and do some more margin without having to reparse the CSV. So I like it for that, but it's not distributed, it's not high performance. Actually, data table can parse faster than Feather can read the binary because it's fully parallelized CSV read, right?
But at no point that then this can link
the GPU in Feather is not linked, and data table is also not linked to the GPU. They're all independent right now. So you have to go into Python, make a NumPy array, and upload that basically into the GPU. There's a bunch of overhead. The goal of this GPU Open initiative is to remove this bottleneck of going back and forth.
For different GPUs, for different rows of GPU, it will do some small compilation.
So it finished. This is the XGBoost speed up of the histogram. So this took 9 seconds this time, not even 10, but the exact one was 212. But 150 for the approximate. This would have been the default on the CPU. So now it's only 16x or so. And then at the bottom is the H2O version of everything. Oh, it's still running. This is running the approximate CPU one, so you can see how busy the XGBoost algo is. It's not that busy, so it's not very efficient either. So this has no chance against GPU.
while we are waiting. Do you have any experience running this on KNLs?
KNLs?
It's a nice lightning architecture.
Nice Lightning, oh, the next gen Intel. We don't have that yet, right? In the document. So we don't have access to any hardware previews, let's say. But I would love to see. I saw some benchmark that leaked earlier this week. I think it's like 50% faster or 100% maybe if you're lucky. So it could be a 2x speed up, but it's not going to be 10x, right? And the Volta that comes out is another 50% faster than these Pascal cards. So everybody has another card. But it would be interesting to see if you could write an algorithm that runs on Google TPU or something other than TensorFlow, right? Because using TensorFlow for gradient boosting might not be very efficient. So I don't know who's going to write a XGBoost for TPUs. If you could, maybe that would be even better, right? Or maybe Google has it internally. It's hard to get anything out of Google unless they drop it out. We can make an ASIC for GBMs, yes. It's a lot of if-else, right? It's really just, actually all the branch prediction is useless because it's usually wrong, right? Because when you split in something, who knows where it's going. So we should actually turn off the branch prediction and just say, okay, just don't waste any cycles trying to be smart.
If you want to do your own ASIC, well, what special function you simply need to add into it.
I think AI in general dictates what the hardware has to be. So hardware vendors now are looking at AI because it's a workload that's gonna drive the hardware development. Right? They're changing the chips just to make this stuff run fast. And it's mostly just deep learning at this point. But I think this is also useful.
Are you guys looking at the new
AMD chip.
The Ryzen 1800X or something. I don't have one yet, but it's like $400 or something, $500. So it might be fun to buy a box just to have one. Yeah, you should get one just for benchmarking.
You mentioned earlier the difference between the 4.7 versus the Xeon, that this was not up to par.
Right, yep.
Yes.
Did you use the native, the math library and things like that for the Xeon? They have special.
So we're talking about the
Okay.
We're talking about the XGBoost CPU histogram implementation, and I spoke to the guy that wrote it, and he did actually try using MKL. He tried to represent the histogram aggregation as a sparse matrix multiply, but apparently even the sparse matrix multiply in MKL does not scale linearly with numbers of threads. Yeah.
Well, that was very surprising. The 4.7 is faster than the Xeon.
It's just because the implementation might not be smart, right? It might say you all do the same thing, and then it gets just slow or something, or it might block, or whatever. There's many reasons why it could be bad, right? And I think you know it, but I haven't looked at it. I'm just speculating. But you can screw up yourself by accessing the same memory with too many guys that all want to write to it, and then they all invalidate the cache lines and so on. So in general, it's not unheard of. It's not the chip's fault. It's just the user that called the wrong.
But it's a big problem.
It's a problem. How do you optimize on a multi-core system? If you have gamers that only want one core, right? For example, all the games are written for one core or two cores, and now you have a 12-core Intel chip coming out, and nobody knows how to write the software yet.
So you had more memory and you had to repeat
If you have more video RAM on the GPUs, so let's say the next gen has more RAM than 60, like a TPU at Google has 64 gig already each, right? So let's say NVIDIA comes out with 64 gig cards, the Voltas next year or something. And you get 16 of those. Suddenly you have 2 or 3 terabytes of RAM on a GPU. It's all shared with like NVLink, which is hundreds of gigabytes of cross-sectional bandwidth. That really is a petaflop supercomputer in a box, right? With terabyte of RAM, you can do a lot of stuff with that. So then you can buy 1,000 node Hadoop cluster, it'll never catch up, right? Basically. So it's kind of significant. Of course, it's not cheap. I think per dollar, Intel might still be better, right? If you care only about the per dollar, but it might not, depending on what you do. Like 10x speed up on a $700 GPU is significant. But if you buy a DGX1, then maybe that's too expensive, right? If you're only looking at commodity benchmarks, like I can buy a $200 Ryzen chip AMD, it might be better per dollar than a DGX1, right? So it really depends on what you do.
Each CUDA core, right? I mean, NVIDIA CUDA core, that more video RAM, the performance will be getting better. Other than
oh, I see. Whether you would want to have more cores on the GPU or more memory per core on the GPU, I don't know. Maybe Rory might know what would actually help.
Both.
Usually it's both.
Basically, both.
Both of those things are increasing fairly dramatically. After they started doing stacked memory, I think the next generation of cards will have 32 gigabytes of video RAM, and they're also cramming more and more CUDA cores into their processors as well.
So how you optimize or
Are you asking me how does that change the way that we optimize?
yeah, how you optimize each CUDA core to how many video RAM, video memory?
Right, so when you launch a CUDA program, you launch it in such a way that all the threads run independently, but they're not all running simultaneously. There will be some small subset of 1,000 threads or something running at each time, and those 1,000 threads will each load cache lines of memory out of video RAM and do some processing on them. And then while it's waiting for that memory to load, they'll load other pieces of memory and things like that.
What networking layer do you use, API or testnet or distributed type of computing? What network framework do you use for distributed computing, API, testnet?
Right, for an XGBoost, the original author of XGBoost wrote a separate library called Rabbit, and it's kind of encapsulates MPI and Hadoop and Spark and all that kind of thing. So we have an implementation that's kind of agnostic of a whole bunch of distributed. Yeah. So XGBoost distributed can run on MPI and Spark and a whole bunch of things.
Just message.
Okay.
Message queue. Message fast.
Yes,
Yeah.
correct. All right, so I think so it finally finished, and we got the 200 seconds for the CPU. Again, if you're smart, you can get it down to 100, but nothing can get it down to below 30, right? Obviously, other than the GPU. But this is still some overhead here. So you saw the XGBoost plane outside of H2O, I think was faster than 30. It's like 10 or so. Yeah, 9. That's what I remember now. Okay. So we have some overhead in H2O still, like something is making it slower, but the actual D matrix creation was only 3 seconds here. So it should have been only like 12 or 13 in H2O, but it was 30. So there's some overhead for this data set where I have 3 million rows. I think most likely is me being stupid because I'm saying, as I make the D matrix, I allocate 200 megabytes, fill that up, and if it doesn't fit, then double it up and copy it over, and then fill the rest, and then again and again and again. That's not necessary. You could log the data once, look at the weight column, all the guys with non-zero weight gives you a row, then allocate this many, and then log it again and fill it up. You don't need to do like one pass to blow it up. I'm just doing this one pass because the weights could all be 0 and 1 because of cross-validation, all that stuff. You don't want to allocate all the data points, only the ones that are used for this computation. So what I really should do is do 2 passes with the weight column check first to avoid the memory code. And the next step is to make the D matrix to have bigger data than what fits in a float array. And then the next step would be distributed XGBoost, where each node brings histograms. And that might be even an easy way for us to, like, once we have multi-GPU per node, it might be done already because Rabbit would take care of the reduction, and then all we have to do is just launch it on multiple nodes. So it might be getting to the multi-node, multi-GPU case faster than you think.
Hopefully 6 months.
So yeah, by Christmas, hopefully we'll have a nice present. An EGX under the tree, right? And then the algo comes for free. Okay. Well, thanks so much for coming. Thank you.
So 6 years ago, I came up with like a proprietary algorithm for XGBoost where I was qualifying the split point with some statistics, and actually had to run first Monte Carlo because it wasn't like analytically it was very hard. Sorry?
Is it like Baruta?
Baruta, I don't know.
Baruta is also something like that.
Let me check.
Yes.
And so what I found, it actually was better on evaluation of the first, like how page ranking, and it was particularly page ranking. The only problem it was several times slower than the.
I see. It was too expensive to do it.
Our algorithm was optimized. It wasn't classical XGBoost, and it was proprietary algorithm also. But it was basic XGBoost just optimized, and.
Baruta, sorry.
Baruta. Okay, let me check that.
This is a feature selection thing, and they also do random. They do a random shuffling of certain columns, and you see how it correlates, and then you do feature importance of the random forest and all that. And see
I did feature importance, but another thing I was doing just the split itself. When I was determining where to do the split, I had a qualification curve that, for example, splitting at the very edge is always, it has to be, the threshold has to be much higher on this
Yes, that's a good idea. And I was thinking about it earlier because we do greedy splits in H2O always, and I'm saying exactly what you're saying.
Yeah.
Don't split the outliers off.
Right.
It has to be worth it.
And so I could, I mean, I haven't worked on it for like 6 years. I can look at it because I'm curious if it could be put on the XGBoost and and GPU, and then the slowness may not be as important.
Yes, maybe you can afford to do more math on a GPU.
Exactly. Yes. So can you take me with his business card or something? Or should I talk to you if I outside?
So either one is fine. Okay. So H2O is open, like it's easy to find, right? There's also message online, Google Stream and all that stuff. We can post an issue on GitHub on the XGBoost. Just make an issue in GitHub, right? And you can just say, hey, what have you thought about this and this? But yeah, there's a lot of options. But then you basically have to find somebody to do the work, right? If you're not doing it, so that's the hard part. So there's like 500 issues, right? And you can just raise another one saying, hey, what about this and this? And somebody
I'm not. Well, this is mostly for H2O users.
That's for XGBoost developers, really.
It's XGBoost developers. Okay.
So somebody might want to do it if you have a good idea.
Right. Okay. Thank you.
Sure.
Arno, nice to meet you. I'm Carlos, and I work with Hewlett Packard on the HPC. So actually, I came via the acquisition of Silicon Graphics.
Okay.
I'm sorry I didn't see you guys. Well, we had good beauty in the GTC conference, but I knew I was going to come to this meeting, so I said I'll just go when I see them. But no, very cool what you guys are doing. Probably I'll send my link in to connect. But have you guys started to check the unified memory direction
yes. I just want to use that actually for the multi-GPU case.
Exactly, because
easy,
I
right?
think
you don't move data. You just you
let it page.
You let it
page. It's fantastic. I think that's going to be really cool. And with SXM2, with the NVLink, that's good. I think. Well, actually, now I'm putting some pressure in the company, so we pay a little more attention because
it's easy to prototype something with unified memory, right?
Do you know we're moving to a cache coherent memory, exascale.
Yes. You'll have
the UV system. Have you seen that one?
The what's the memory? The memristor stuff too. Right?
Exactly, the NumaLink stuff. Actually, I just showed your link in it. You were at the SLAC, right?
Yes.
Right. I used to cover SLAC years ago, but just this month we're going to install our system is called the UV, the Very Scalable Shared Memory, for the Center of Personalized Medicine. I think those guys anytime will jump into more of these machine learning type of stuff because it's very natural for medical cases and things like that. But they got a machine with 320 cores, 10 terabytes of shared memory. It has 4 GPUs, could have more, and 20 terabytes of NVMEs. So your data could live inside the memory without ever leaving.
Yes, you can do whatever you want.
Yeah, that's one direction. And the other, actually, we were showing this at the show, the new board.
Is that really memristor stuff?
I'm sorry?
Is that memristor stuff?
No, that's because, that's the
this guy. Do you know this guy, Gergely Zimani?
No.
He was working on memristor stuff, magnetic. Like he was working with HP, I thought, even on memristors one day. He was presenting at SLAC 10 years ago. Maybe something else, but he's doing this physics, all the magnetic stuff. But that his knowledge was used to actually make these systems, right?
We'll keep our direction of moving to memory-centric computers.
Is it SSD-like?
Well, no. The one I'm telling you with the 10 terabytes of memory is DRAM. So regular 32 gigabyte DIMMs or 64 gigabyte DIMMs.
But then the other one, the NVMe, what is it called?
The NVMEs are the Intel SSD drives, which
so
are
commodity NAND.
It's commodity NAND inside a PCI slot, and we have
NVMe, of course. I have
NVMe. So we have 20 of those.
2 or 3 gigs write rate per each.
Exactly. But you are right. What's coming is, have you seen the cross-point technology?
No. That's the...
Memristor was going to be HP's gamble into this area. But now,
you can just
cross-point. cross point catch up.
What does that mean, cross point? That's CPU to main memory?
No, that cross point is a type of memory where they hold the bits like.
Oh, it's 3D or something?
It's 3D. It's 3D. But the beauty is that it's faster than flash memory, like 100 times faster, and it's 100 times slower than DDR, right? So it's like in the middle, but you have the density and price of this one, but you have 100 times more.
So I could even buy 10 terabyte of it or something for my home PC at some point.
At some point, but and it had sort of beauties because if you have let's say you have a terabyte process running, and the machine crashes, but this new generation, this is what's coming for next year, big time. Enterprise storage memory or something like that. So with that, exactly, and we're going to have something that allows you to do like RAID in memory, right? So now you have like something like the disk, but with the speed of the memory.
1 or RAID 0 or RAID 10 or something? What kind of RAID mode would you say?
It's like RAID 10.
Something that's somewhat redundant and fast.
And they have another technology that I just showed that it's really cool because it's like they have a small battery in the DIMM that has part DRAM and part flash. So if something breaks, it has enough time to offload everything to memory, and then the system dies. But when you power up, everything is there. Exactly, everything is in flash again.
But you can take the power out,
exactly,
plug it back in, and say go. And
but now you don't need these gigantic UPS to keep the system alive. Exactly, that's expensive. Yeah, it's a small thing to keep the team alive.
You can even fill this capacitance almost with like real, like you can fill it all the time and it's running like a little capacitance. Right?
Exactly.
It doesn't have to be real batteries or whatever. You can charge it while it's running.
That's exactly.
Okay.
That's coming next year, and that's going to be really cool. And the other thing we were showing is, I don't know if you have seen the guys at Tsugami, the Tokyo Institute of Technology. They just have a big system, but their whole mindset is in artificial intelligence, deep learning, this kind of stuff. 2,000 GPUs. But the thing is, the professor there was showing that they have seen that once you have to go outside the GPU, exactly what you were describing, once you go outside the memory, the efficiency goes down. So when you want to scale to that size of problems, they wanted to have more connections out of the board. So we designed for them this board with 4 P100s connected via NVLink,
but also to main memory.
And each one of them has a PCI Express connection to an OmniPad. So it's 4 connections per board instead of a board with CPU and one InfiniBand. It's 4 connections for each one. They connect all of those guys.
But you get 50 gig a second outside of connections.
Well, it's 400 gigs out of the board because it's 4 of 100.
Exactly. 50 gigabytes a second. It's just like main memory.
And then we have a chassis that is 9 of those boards in like 10U, and you can have 4 of these in a rack. But probably the calculation you are making is 300 watts per GPU. That thing.
20 kilowatt power.
The racks are between 60 and 80 kilowatts. It's brutal, right? And it's water cooled. So that's, well, I come with the SGI acquisition, Silicon Graphics. So our water cooling technology was really good. And so that's what HPE is.
At home. I want to have water cooling. It feels cool.
Water heating.
On the outside of like a big fan.
Yeah, wow, those things are noisy and all of that. But I was amazed when I saw the board and the way they architected it. And that is going to install, I mean, they were building the boards probably next month. We will be doing all the releases, but that's, but you can see that this thing is coming all over the place. So yeah, so I wanted to come and see your presentation and get familiar because I want to keep track on what's going on. And Yeah, but I see that your approach is more to the shared memory side and that you use all of those techniques. So I don't know. I'll just keep in touch. But if you need to test something in one of the big systems or what, you know, sometimes it's hard because you cannot develop if you don't have the system. But nobody will give you a system if you don't have the application. So sometimes somebody needs to break this. Okay, let's try this and see if that works. So
if you have resources that want to give us access or something, or joint showcase that it's a good hardware or something, we have collaborations, right? We partner with NVIDIA, with Intel, with IBM.
That's what I was thinking.
Amazon, everybody. So
those guys from Nimbix are really cool.
Yes, exactly. And if you have like an HP,
we have a benchmarking center. And we have systems there. So usually it's like, okay, tell us what the case is, what you're going to, but if you say, hey, look, Carlos, help us get a couple of terabytes of memory system so we can try this, probably that's something that, okay, how long is it going to take out? 8 hours, right? Okay, at least you run it and get your result and justify things. Or that system at the Stanford, they're looking for partnerships. That thing is huge. It's 10 terabytes of memory, and they are looking for projects. Obviously, they are in the personalized medicine kind of stuff, but they want this thing, you know. They wanted to shine, to publish things.
We have 3 Stanford professors, right? And our
Australia for a while.
So Hasty, Sharani, Boyd, all these guys.
The system will be located in the SLAC data center.
What are you doing?
So it's co-located there. Feel free.
Reach out to them.
Well, that's what I'm saying, because I mean, sometimes a collaboration, something, they want the system to be used. And if you come with a problem that they can chime to, they will be happy to. Exactly. So I think I have another couple of systems here in the Bay Area, and also for bioinformatics. One is doing proteomics, and they have like 8 terabytes of memory, and another guy is doing metabolomics. So all of those startups that are doing like new cancer research, and they are funding candidate drugs, and like crazy. So their test was, Carlos, it's in Python and we don't have time. So it's breaking.
The hardest part.
Show me that you can run a 2 terabyte of memory matrix, and we need the system tomorrow. And say and done. We run the benchmark in 1 hour. It was just NumPy, create the matrix, multiply. That's it, done. That's done. That's it. You don't have to worry anymore about the system.
It's good to have one system log in, you do it, it's done, right?
Yeah, some people say there are more
cores are
memory efficient way, but
you don't need to worry about distributing and all that.
Exactly. But I think that's what unified memory is going to help a lot with. I was seeing at the conference they had a couple of presentations about the paging mechanism and all of that.
Cooperative groups, you put a line, you can actually have the different warps, 2 different kernels and all that on the unified, like all smart stuff. You can tell what to do what. Now I need to learn CUDA programming, because I did C++ for 10 years, and then I did Java for the last 3 years. Now I need to say no more of that, I need to go back to C++, but I can learn it, but CUDA I haven't done much.
The interesting thing I'm starting to see is well, I'm debating myself, because I want to retrain myself in some things. But
so you're talking about
what's the or API the other API that uses distributed computing, heterogeneous computing, OpenCL.
OpenMPI.
No. It's OpenCL where you can target actually anything, but you can compile and you can target different architectures. So you can say, this is my regular code, and then this core I'm going to send even to an FPGA.
It's just like LLM.
Exactly. So you plug that kernel into the main system. So I have seen that people is going there for because now
If your data is on the card,
combination of CPU, FPGA, that is fast coherence. You started to be really interesting. But GPUs are smoking everything. It's too fast.
That stuff is hard to develop, right? Because you don't know yet. CUDA is easier because there's so much code out and 10 years of experience.
So
I tell everybody that's what they did really well. Build the ecosystem for the developer, make it easy. Hey, look, this is sample
They're all
code.
closed source, right? They're assholes and still got away with it. Linus Torvalds, he hates NVIDIA, right? Google Linus Torvalds and NVIDIA video on YouTube. He made some funny video on video.
Oh, really?
He really is angry. So, but still, they got away with it, and now everyone likes it because they have the cool technology.
Yeah, it's really cool. It's really cool.
Yeah,
They are hard and burn a lot of heat.
that's a really good
You can use it for gaming and for AI, right?
Yeah, no,
That's why they get the volume.
I was thinking a lot of deep learning, but I like a lot the approach you
Yeah, I
show
mean,
today.
we have deep learning too, right? If you go to if you go here and you select deep. They're using this Wi-Fi thing, it's really slow.
Oh,
It's internet, it's over cell phone. So if you go here to model DeepWater, then you actually have the same everything, but here is a backend MXNet Cafe or TensorFlow, right? And this is using GPUs, right? So I can show you the GitHub.
Yeah, that's good fun. There's some cool languages coming out, like stands, one of those languages, which is like a lot of maths. Probabilistic languages.
Yeah, I've never heard that. Probabilistic language, it sounds like.
So there is a TensorFlow multi-GPU.
Yeah, it's pretty crazy.
So you can do all kinds of cool stuff. So you can literally load the DeepWater estimator, and then you can make your Keras graph. This is Keras using all this stuff, right? Which is deep learning, obviously. So you can make your own graph with everything in TensorFlow, and then you save it to a file, and then you tell H2O to read this file in and run.
And that's it.
And then it runs on 2 GPUs. So it's pretty cool, like the technology is there, right?
Well, my concern now is more philosophical because
To know what to do now. It's almost time running out for you to learn what to do, right? For everybody. Like we don't know what's next. Google is taking over and everybody